Today I'll be presenting on the surface attachment of small molecules to metal oxides through diazo coupling. Molecular surface attachment has applications in many fields, including nanoelectronics, semiconductor coatings, photodynamic therapies, and more. One major field where surface attachment is needed is solar energy conversion devices, and specifically water-splitting dye-sensitized photoelectrochemical cells, pictured here. Strong, stable surface anchorage of dyes and catalysts is crucial for the long-term performance of these systems. This present work utilizes the silotrane anchoring group with its structure shown here, which is a triethanolamine protected siloxane. Not only does it form strong, very stable silyl-ether surface bonds, but molecular silotranes have a much longer shelf life than their unprotected counterparts due to limited hydrolysis and oligomerization. Modifying molecular species with anchoring groups comes with synthetic challenges and limitations that sometimes prohibit stable surface anchorage. These challenges can be sidestepped through the initial installation and subsequent reaction of a functional group anchored on a surface. Click chemistry, amide coupling, and nucleophilic substitution reactions have been studied on surfaces for this reason. Here, we look to the diazo coupling method, which has not yet been utilized for derivatization of metal oxide surfaces. This reaction is attractive because of its synthetic simplicity, using cheap and commercially available reagents, formation of the strong, stable azo linkage, and its potential for light harvesting applications. The generic scheme for the molecular reaction is pictured here. To apply this to surface chemistry, we first installed amine groups to titanium dioxide thin films through the sensitization of 4-aminophenylsilotrane, which was confirmed using X-ray photoelectron spectroscopy, visualizing the nitrogen 1s peaks. Next, the amine was coupled to 2-naphthol using the diazo coupling method shown in this scheme. Citric acid buffer and carbonate buffer solutions were used to obtain more mild pHs, since the extreme pHs typically used would promote surface detachment. The UV-Vis spectra show that after coupling, the absorbance of the film is moved into the visible region, indicating successful dye formation. Diazo coupling is applicable to many activated arenes, typically containing amines or hydroxides. To demonstrate its widespread applicability, we coupled both aniline and phenol to the surface-bound aromatic amine. Although some of the absorbance is masked by the TiO2 film, the increase in absorbance in the region shown indicates successful coupling. Shifting gears now to surface loading. It is typically most favorable to load as much substrate as possible to the surface. It has been shown, however, that when using silotranes, triethanolamine also binds to the metal oxide surface, but can be easily removed via an acidic wash. To test if the triethanolamine decreases surface loading by blocking surface sites, we performed the coupling reaction 4 subsequent times, removing triethanolamine and resensitizing with silotrane each time. As can be seen by the UV-Vis traces, the loading was increased by a total of 360%, supporting our hypothesis that triethanolamine is limiting surface loading. In conclusion, this work represents a novel method for the stable surface attachment of molecular species using the diazo coupling reaction, allowing synthetic challenges and limitations to be avoided. We suspect this method can be implemented widely, spanning various fields concerned with metal oxide surface derivatization. Additionally, we have found that the loading of these molecular species can be increased by removing surface-bound triethanolamine. Looking forward, we will further investigate loading by adjusting initial sensitization conditions to disfavor triethanolamine binding. We will also look into exploiting the lack of full surface coverage for solar cell applications, where dye-to-catalyst ratios have been found to greatly affect overall performance. Thank you so much for listening, and I look forward to hearing any questions later on.